So what are we learning today? Right, we are looking at magnets that they actually come in different shapes and sizes. Magnets are actually made up of the magnetic material, which is iron and steel. Right, not all, we're going to infer that not all magnets are magnetic, right? Sorry, not all metals are magnetic, and all non-metals are non-magnetic. Okay, other than that, we're going to look at the poles of the magnets, as well as the poles actually have the strongest attraction. Okay, so what is exactly a magnet? Okay, so what is a magnet? It's actually something that will attract or even repel certain objects. So when we talk about certain objects here, we are looking at things like magnetic materials. We are also looking at things that are probably magnets themselves. Okay, so what happens here is, hey, what happened to my highlighter? My highlighter is missing. All right, so it's actually an object that will attract. When attract means it's going to pull, right? So that's why it's pull. If it's going to repel, it's going to push, right? Push them away. So this certain objects here, we are usually looking into, magnets as well as magnetic material. Hey, hold on. What happened to my colors? That's weird. Okay. Okay, when we talk about certain objects here, we are referring to magnets, all right, as well as magnetic materials. Okay. Okay, so magnets itself, they are actually made of magnetic materials, and you can actually make magnets into different shapes and sizes. Right, what you can see over here, you have a bar magnet, right? You have a U-shaped magnet. Do you know of any other shapes? I believe you all played magnets before when you were much younger, probably in kindergarten or even P1, P2. Oh, shoot. Any more? Circle? Sphere? Okay, the sphere magnet. The cylinder-like one, right? The cylinder one is what we call it to be a rod magnet. The button magnet, as well as the ring. I think someone called the ring as the circle. I think someone said circle. Right? Yeah, like cylinder. Didn't say cylinder. Cylinder one that looked like a cylinder is actually what we call a rod. Okay, so those are the different shapes of magnets that we can have. Right? Do you see something over here? Oh no, I can't move this. Okay, so there is something over here. Okay, so what else do we know about magnet? I can go ahead, right, if you need to go to the washroom. Right, most magnets that we are using right now, they are actually man-made. Right, most of the magnets that we are using right now, they're actually man-made. There are things like natural magnets, but we don't really use them because they are found naturally out in the wild. And how did this magnets, or rather, how did the term magnet came about is discovered by a shepherd itself. If I didn't remember wrongly, he's called Magnus or something. All right, living in somewhere in the Greece, right, in Greece. So natural magnets are known as lodestones. All right, so natural magnets are not discovered by a scientist. In fact, it was discovered by a shepherd. Lodestone is actually the name for natural magnets. All right, maybe I can link this down for you so it's easier for you to understand. Natural magnets are known as lodestones. Shepherd is the one that, they chase the sheep around. Demagnetize means they lose their magnetism. All right. So for any questions, this should be quite simple for this page. Okay, so we're going to move on. So there are 4 different types of magnetic materials, right? You have iron, steel, nickel, cobalt, like what you have seen in the animation earlier, right? The Pando, I keep forgetting it's called Pando animation earlier. So, but however, in your syllabus, right, in Singapore syllabus itself, you only need to know iron and steel within your syllabus. All right, and within your syllabus is just iron and steel. Cobalt and nickel depends on your school whether does your teachers want to teach you more. All right, so these 2, nickel and cobalt, I guess we'll put down here, not in syllabus. All right, but it's something that is good to know. Okay, so how can we remember the 4 magnetic materials? All right, so how do we actually remember the 4 magnetic materials? If you notice over here, what does this thing look like? Oh my God, it makes me feel hungry. What does this thing look like? Chicken. Chicken? That's not this look like chicken. All right, so that's one way of remembering them. There'll be I see chicken nuggets. I see chicken nuggets. All right. I know some of your schools teach it as coins, COINS. All right, coins. So that's another way. All right. So yes, then we will come to our first bubble question. All right. So let's come to our first bubble question. I cannot remember how long is this bubble. This bubble is only 30 seconds. Yes, this one is easy. They're asking you which of the following is a magnetic material. Okay, this one is easy, right? They're asking for magnetic material. Right, they're asking for magnetic material. So the only magnetic material you have here is actually steel. Right, it's pretty obvious. All right, so what are all these materials known as? No, yeah, wood, glass, and plastic. What do you call them? Call them as non-magnetic materials. Okay, so we have magnetic materials and non-magnetic materials. Other than that, can you name me other non-magnetic materials? Paper, very good. Any more? Oops, I can't write. Paper, fabric, ceramics, aluminium, what's that? Aluminium, copper. Okay, hold on. I realize my screen is half blocked. Copper, gold. Someone said gold, silver, rubber, diamond. Yes, yes, so many materials, right? Right, there's so many things that are actually non-magnetic material. All right, so you have all the different non-magnetic materials, right? So there's so many around us. Yes, steel is actually a metal. So when we talk, we cannot be putting down a material as metal over here. If you're going to put down as metal, you need to be specific. You need to be very, very specific because not all metals are non-magnetic. Because we have things like with the four magnetic materials, iron, steel, nickel, cobalt. The four magnetic materials are actually metals themselves. All right, so if you're going to write down metals, you may not get your mark. So you need to be a little bit more specific when you're talking about the term metal. So we try not to use this. All right. Okay, then we're going to move on to the next concept. So we're going to look at characteristics of a magnet itself. So if you look at a magnet, I believe I've seen magnets before, like what you can see in the diagram over here. All right, a magnet itself has two poles, right? The north and the south pole. Where is my pointer? Okay, the north pole and the south pole, right? So north pole, south pole, and the poles itself is actually the strongest. They actually have the strongest magnetic strength, right, to attract other magnetic materials. Right, so if the poles means the ends, right, poles, the ends here, the ends are the strongest. What about the center? Yeah, I'm going to put down here, poles of the magnet is actually the ends of the magnet. Okay, if the ends of the magnet or the poles of the magnet is actually the strongest, then what about the center? If this is a magnet, then the poles at the two ends are the strongest. Then what about the part in the middle? What do you think? So it's like, delay is like, Come on, think about it. In the middle itself would actually be the weakest. Right? Good job, everyone. All right. So the center itself would actually be the weakest. In a ring magnet, where are the poles? Okay, in a way, I will draw the ring for you. Okay, give me a while. Let me answer the question at the bottom over here first. Okay, what about the magnetic strength at the center of the magnet? The center of the magnet is actually the weakest. It has the weakest magnetic strength. All right, so if you're going to drop a bar magnet, for example, you drop a bar magnet into a bowl of paper clips, the ends, right, which is the poles, they will actually attract the most number of paper clips, while the center will attract the least or even not attract any. Where is the ring poles of the ring magnet? So let me draw a very ugly ring. Okay. I'm going to draw like a little bit 2D. Something like this, right? So poles of the ring magnet itself, there will always be a pole at the top and a pole at the bottom. So the top one depends on how you flipped it. So I'm just going to put down the top as north and the bottom will be south. Okay, so that is how the pole that is where the poles of the ring magnet are. Okay, so let's move on. Okay, so characteristics of a magnet. All right, what happens if you're gonna break it into two? Okay, it's not that easy to break a magnet, but yes, you can break a magnet. So what happens if you break them into two? What do you think? Will it be like, no, two, but one is totally North Pole and one is totally South Pole? Do you think it's possible? Or maybe you break it, it becomes two separate magnets, or break it and it's no longer a magnet. Okay, in fact, when you break a magnet into two pieces, all right, yes, you may not be able to fix them back. In order to fix them back, you probably need to do a lot of chemical reactions to it. It actually, when you break them into two, they will still be magnets. It's just that you get two separate magnets. All right, so when you break them up, like what you can see over here, all right, the north, you chop, as in you cut the magnet into half, or somehow you broke the magnet into half like this. And what happened here is that the north and then the other end will actually become the south. And here on the blue portion on the right side, this will become the north, and then you have a south. So you get two separate magnets. So what happens when you break a magnet into two pieces? Does it lose all its magnetic strength? This would be a no. It doesn't lose all its magnetic strength. All right. Will change where the north and south pole are? No. The north and south pole remain where it is, just that you're going to have new ones over here. So the first piece will have the north, right? And the other end of the first piece will become the south. And the other piece will have the south, the other end will become the north. Okay, then the last one. Have each broken piece to be its respective pole before it was broken? That will be a yes. Does it have? Yes, because now you are getting two separate magnets. All right, so let me, okay, let's see now. Let me do this. Okay, now I have another diagram down here, right? Let's try a different one. Okay, what happens if this is the south and this is the north? What would this portion be? Let me label this. Okay, let me label this for you so that it's easier for you to answer me in the chat. Can I call this X and call this Y? What do you think X is going to be and what do you think Y is going to be? Can you type down in the chat? X is this, Y is this. All right, so X will actually be the north, like what we understood earlier. Right, you're broken down into its own individual two magnets. So X will be the north, Y would be the south. All right, so let's move on to the next one. That will be our bubble question number 2. All right, so let's look at bubble question number 2. Yes, I can see the panda at the end. Oh my God, the pando. Okay, bubble question number 2. You have 1 minute for this bubble. They're asking which of the following statements about magnets is true. All right, you have 1 minute for this bubble. Let's go. So the answer for this is actually option number 3. Oh no, the color is not nice. Okay, option number 3. Okay, why? Okay, we'll look into individual options. Okay, why are all the other statements are wrong? So for the first statement wise, for the first statement, we understand that not all magnets, all right, are natural because we have man-made magnets. All right, so the part on man-made magnets. Okay, so that's the first thing. All right. Next, they ask, magnets can only attract objects. The thing is, it's not just attracting objects. Magnets can only attract magnets as well as magnetic material. So magnets can only attract other magnets and magnetic materials. Okay. Then what about the last one? Okay, option 3 is correct because we know that the magnetic strength of a magnet is the strongest at the poles, right? So the last option, it talks about larger magnets is stronger. It may not be true all the time because sometimes there are very small magnets that are really, really very strong. So the size or the length, sometimes no longer magnet, so you just give you the size of the magnet doesn't affect the magnetic strength. All right, some bigger magnets are actually weaker, some smaller magnets are actually smaller. Okay, so I'm going to put down just in case you want to take a screenshot of as notes for you all to revise on later on. All right, so size of a magnet does not affect its magnetic strength. All right, so far so good. Okay, so let's look at bubble number 3. You're going to drop, lower a bar magnet into a tray of steel paper clips as shown below. All right, so they tell you they're going to lift it up and ask you what is the most likely the number of steel paper clips that's going to be attracted at X, Y, and Z, the different parts of the magnet. So you have 1 minute for this bubble. 1 minute for this bubble. Let's go. Okay, what can you recall about the strength of a magnet itself, within the magnet itself? Characteristic of magnet itself is that it's always strongest at the poles. Okay, I'm going to put down here, magnetic strength is the strongest at the poles. Magnetic strength, strongest at its pole. And of course, we know that the weakest is at its center, right? So middle center is the weakest, so obviously Y, it has to be the weakest, and X and Z would be the strongest. But sometimes when you look at the two poles, maybe the two poles, the ends itself, they may not be of equal strength. It's perfectly fine, it's normal. All right, so with that, your answer will actually be number 3, because we need to look for the weakest one. Okay, I have one question for you. What about the U-shaped magnet? Will it still be the same answer? In a U-shaped magnet, it's the same. Right? As long as it's the poles will still be the strongest. So having said poles will still be strongest, meaning that Y and Z here will still be the strongest. Right? And sorry, X and Z will still be the strongest. Y would be the weakest. Right? So it will still be the same as the bar magnet. All right, it still be the same as bar magnet, just that it's curved. Pendo recalled something. Okay, he recalled that he was in a school festival. He placed a small plastic box with a ball bearing on the table. Then he slid the bar magnet along the side of the box as direction is shown, right, in the diagram. Right, so the ball bearing actually moved. Right, it moved. So what I thought this really rich. Which of the following materials could the ball bearing be made of? Can you think about it? The magnet. You have 1 minute for this bubble. Let's go. Okay, so which material could the ball bearing be made of? So the ball bearing itself is being attracted to the magnet. Okay, so we can put down here because it followed. The ball bearing followed, move along with the magnet. So it shows that the ball bearing attracted. Okay, attracted to the magnet. So in order for it to be attracted to the magnet, it has to be made of a magnetic material. Okay, so this one must be made of magnetic material. Okay, all right, so with that, our magnetic materials is pretty obvious, it's iron and steel. These two are magnetic material. Okay, while copper and wood, these are non-magnetic material. You all probably got tricked by copper, right? The other magnetic material that starts with a C is actually cobalt and not copper. So with that, your answer will be number 1. Okay. All right. So let's move on. Okay, we have 4A here. The setup below shows a magnet. You can see the magnet is suspended here. All right, and you realize that the paper clip was floating. All right, why is it able to float? What do you think? Why is the paper clip able to float? What? Paper clip floating? How? Yeah, the paper clip is being tied to a string and of course to a glass block so that it doesn't fly away. All right, magnet here, and you have a paper clip. Okay, so the idea here is why the paper clip is able to float up because it got attracted. Right, it's being attracted. Right, let me write down here. Right, attracted to the magnet. Okay, it's attracted to the magnet. However, it couldn't reach to the magnet. It couldn't reach to the magnet because of the string. Right, that's being tied to the glass block, so it couldn't fly away. Right, so it got attached. So there's a limited length to the string. Right, so that's why it's actually floating. Right, it's not attracted to the magnet itself. Okay, so identify a possible material for the paperclip. Yes, it's going to be iron and steel. Right, it's iron and steel. Right, you can also put down cobalt, right? The other two, right? Cobalt and nickel. But do take note that some schools do not teach you cobalt and nickel because it's not within your syllabus. All right, if your schools are really, really very strict, you have to stick it to steel and iron only. All right. Okay, so next. Now, this time around, yes, you still have the same setup, right? It's still the same setup. We know that paperclip X is floating in air because paperclip X is actually a magnetic material, so it floats up. But this time around, you're going to replace it. You are replacing it with paperclip Y. And they tell you that paperclip Y did not float. Why did not float? Think about it. Why is it not floating now? Why paperclip X can float and paperclip Y cannot float? What do you think? All right, so why it didn't float? Think about it. Initially, if you look back at the very first part, we understand that paperclip X was able to float because paperclip X was being attracted, right? So we're going to put back down here, paperclip X floating because it got attracted. Attracted to magnet because it's made of magnetic material. It's made of magnetic material. But this time round, paperclip Y didn't float. So the only reason you can think of that causes it not able to float is high chance paperclip Y is actually a non-magnetic material. All right, most likely it has to be a non-magnetic material. Okay, so paperclip Y made of non-magnetic material, so it cannot be attracted by the magnet. Okay, this is really easy, right? All right, now you have a horseshoe magnet. They're asking you, you drop this horseshoe magnet into or rather you brought it near a tray of pins. So which part of the magnet will actually attract the most number of pins? I like to say bubbles, but this class I call bobas. All right, so you have 1 minute for this bubble. Question number 5. Let's go. Okay, so strongest part of the magnet is actually the pole. So obviously the poles will have the strongest magnetic strength. So it will attract the most number of paper clips. So answer is number 4 because D is the pole of the magnet, which actually has the strongest magnetic strength. Right, so this is easy. Okay, so answer is number 4. Then let's move on to the next question. Aha. Now you have a bar magnet, you break it into two. So what are the poles of the broken pieces of the magnet? Right, so you need to think a little bit. This is easy. Actually, you have 1 minute for this bubble. Before I launch, just to let you know, what does it mean by demagnetize? All right, demagnetize it meant that the bar itself is no longer a magnet. All right, you have 1 minute for this bubble. Let's go. Demagnetize is spelled wrongly. Right, so when you cut the magnet into two pieces or break it into two pieces, it will break down. It'll be broken into two separate magnets. So with that means that you have the south north pole here. So the other end of the broken piece would actually be the south pole, and it's the same for the other portion. All right, so the other portion here, this will be the north, and this will be the south. All right, so with that, your answer will be number 2. Let me change the color for this. Okay, it'll be number 2. Right, so let's look at a Pendo recalling question again. He recalled something, some game. All right, so he moved on to another game store. So just now he was at a game store, now he's moving on to another one with the magnetic fishing game. I believe you all played that before, right? No, sometimes maybe your parents bought you those games, or maybe you go out and play those games before where you have this magnet and then you try to attract the fishes. So at the end of the fish itself, all right, and what do we know about iron? Can you tell me something about iron? Got to do with magnets. What do you know about iron? What type of material it is? Good job. Right, it's actually a type of magnetic material. So iron, I should circle. Okay, iron, magnetic material. Right. So obviously, when you bring the magnet over, it will be attracted. All right. So Panda wonders how he was able to pick up the wooden fish using the fishing rod. So it got to do with iron being a magnetic material, and of course, the magnet will be able to attract the iron piece. So hold on, I cannot click. Okay. So how do we actually answer this question? We need to talk about the material itself, iron being the magnetic material. Do take note, you cannot put down as iron is magnetic. You get it wrong. Because it's a different meaning. When you say something is magnetic, it means that that object is a magnet. So this iron piece on the wooden fish is not a magnet. It's just a magnetic material. So the word material here is very important, right? The word material there is very important. So you need to state down as iron is a magnetic material, right? So the magnet is able to attract the piece of iron. So that's how it's able to pick it up. All right, so far so good. So next thing after Pando left the storekeeper decided to do something. He's going to change some of the wooden fishes, right, with other wooden fishes with copper tip. So this time around is copper. Copper. So will you still be able to attract the fishes? All right, so no, right? Why is not able to? Why no? Hannah is like, no, 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 no. Why no? Why not? Daniel said no too. Hey, why not? Why Pando will not be able to attract the fishes now? All right, so now it's going to have copper, right? Copper itself is actually a non-magnetic material. So you need to mention that it is a non-magnetic material. So if it's a non-magnetic material, it will not be attracted by the magnet. Right? So we need to answer the first part of question first. So will he be able to do so? That would be a no. Why no? Because copper is a non-magnetic material, right? And copper at the tip will not be attracted by the magnet. Okay? Okay, let's learn some fun facts, something interesting about the names or poles of a magnet. So we don't just call it North Pole or even South Pole. You can actually call them as the north seeking pole, right? North-seeking pole as well as the south-seeking pole. Right? You call them that is because they will always be searching for the north, seeking the north, as well as seeking the south. So that's why you have the name called north-seeking pole and south-seeking pole. Right? They look for it. Seeking is like looking for it. Okay. So with that, one more bubble. Haha, this is a slightly more difficult bubble. All right, so you have the diagram below. It's actually a magnetic separator. It separates magnetic materials from non-magnetic materials as they move on the belt. All right, so they tell you in the diagram here, this is the magnet itself. You can see that some will drop into container A and some actually drop down to container B. So they ask you which of the following materials will be collected in container A and container B respectively. You think it through. Think it through. All right, you have 1 minute for this bubble. All right, 1 minute for this bubble. Let's go. Okay, so let me explain what's going on. All right, so you can see that you have magnet here. So what we know about magnet is that magnet will attract the magnetic materials. So this portion here, notice that this portion here is still being attracted to the magnet. So as the belt moves away from the magnet, it actually drops down. All right, it's going to drop down. So what's going on here? This part is attracted to the magnet, meaning that it has to be magnetic material. Okay, magnetic materials. So container A will be all the magnetic material. Oh, no. And what about container B? Container B, you notice that it's not attracted, then you just drop down into container B. All right, so container B would be not attracted to magnet. So they are all the non-magnetic materials. Oh no, I can't squeeze my big handwriting in. I just put down here as non-magnetic material. All right. So with that, I wrote material. No, I did not wrote material. Oh, I did. Oh dear. Me. I can't erase this somehow. Hold on. Hold on. Okay, never mind. I shall cancel. Somehow I couldn't erase. Okay. So with that, all right, I will underline the ones that are wrong. Like, container A is not all this. Container B will not have aluminum. Container A will not have aluminum. Container B should not have magnetic materials. And should not have iron. Yeah. So with that, your answer will be number 2. All right, you'll be number 2. Okay, I'm ending already. So where do you use this magnetic separator? Right, it's actually used in those metal containers that, you'll find a product, you want to separate out certain things. Okay, so that's why they actually use a magnetic separator.